Good evening, students. Welcome to today's class. So already we have seen branch and bound and traveling salesman problem. How can we solve using branch and bound approach in previous class? So here I am briefing about that approach and also traveling salesman problem that I already completed and going to the next two methods, that is FIFO based and LIFO. In the least cost based 0 knapsack problem, how can we solve it using two different approaches? So this is already told branch and bound, that is always used to solve optimization problems, not feasible solutions. And always when we are solving a problem using branch and bound approach, the problem must be a minimization problem, not maximization. So if the problem is maximization, first you have to convert that into minimization, and next you can solve it using branch and bound. So this is the introduction, and next an example, how can we solve. And our general difference is branch and bound is always used to solve the problems using breadth first search instead of depth first search, where backtracking uses the depth first search approach. So these are the already definitions we gone through the earlier class, that is what are the active nodes, live nodes, C nodes, dead ends, and also extension of the state space tree for any problem. And this is an example of FIFO based least cost based or any other type of branch and bound techniques allowing a state space tree construction. So coming to the two methods, that is the least cost based and also FIFO based branch and bound techniques. So this is the first one. This is the least cost based FIFO based. This is the FIFO based branch and bound technique. So FIFO based branch and bound technique means when we are constructing the state space tree using branch and bound technique, here always we have to expand node using breadth first search, that is in first in first out. So here we are expanding node 1 and next node 2, 3, 4, all the branches available from node 1. And next go through the expansion in left to right out. And next from 2, 5, 6, and from 3, 7, 8, from 4, 9. And next again expanding from 5, 10 and 11, from 6, 12, etc. So here means the FIFO based branch and bound technique cannot allow any proving approaches. So we have to expand the nodes continuously. But when we are coming to the FIFO based approach, last in first out order, the traversal evaluations, the expansion of state space tree is same. But here in FIFO based branch and bound, we are using queue structure. So first one is already processed. So what are the branches to 1, 2, 3, 4 that are inserted as E node in the queue. And next, expanding branches of 2. Then we can remove 2 and insert branches of 2, that is 4 and 5. And process 2. And next we go to branches of 3 and remove 3. Those are nothing but after processing the branches of the relevant nodes, then you can eliminate those. So you can insert 7 and 8 and remove 4. And next coming to the, that is first branches for 2, 5 and 6 and remove 2. And next branches for 3, 7 and 8 and remove 3. And next branches for 4, that is 9 and remove 4, and etc. Continue in this manner until Q, that is the number of possible state spaces available in the set. And next we coming to the LIFO based branch and bound. Here we are using a stack instead of a queue. So here always we are crossing the elements from the top of the queue, but the elements are listed in this LIFO based branch and bound approach using depth first search. So always insert the nodes depending on its depth value in the leftmost part of it. So here first we are expanding, we are starting 1 and next left node of 1 is 2 and next left node of 2 is 5 and left node of 5 is 10. So if this is the terminal node, then you can go to process the next. So check the stack here. So first one is 1 and next left of 1 is 2 and left of 2 is 5 and left of 5 is 10. So 10 is the terminal, you can stop. And next go to the next one process. So this is the LIFO based branch and bound technique, but this is not suitable in all cases. So third method is least cost branch and bound technique, which is the most appropriate and advantageous when we are comparing with the earlier two methods, because this is always allowing pre-pruning. So no need to allow any expansion if the node that gets a value that is maximized representation or minimized representation. So least cost is always producing a better expansion for the space tree by pruning the nodes, which leads to unfeasible solutions or infeasible solutions. Which leads to infeasible solutions. No need to expand that node, simply expand the nodes which are having feasible solutions. So automatically the number of iterations may be less, and also the expansion of the trees that may be less when we are comparing with the previous approaches. So initially we take one as the node similar to the previous method. Here also I'll expand 2, 3, 4 and next similarly expand 5, 6 of 2 and next possibilities of these. And next, after expanding these, if we can find a solution which is optimal, then no need to go to expand to the further nodes. So here no need to expand the branches of 3 and 4 because the solution is found in 2. Then the tree is pruned without expansion in 3 and 4. So that is the advantageous feature when we are comparing the least cost search with the previous two methods. So in branch and bound, always we can prefer least cost search or FIFO based branch and bound approaches, but among these two also, but we cannot go for LIFO based search. But FIFO based search is always leaving the sum of the nodes and also not producing any efficient optimal solution in minimum time. So these are the three different types of approaches for branch and bound. So coming to the 0-1 knapsack problem. So already we gone through traveling salesman problem. There are two problems we can solve in branch and bound using any one of the three approaches. So already we have solved the traveling salesman problem using the best method, that is the least cost approach method, in previous class. Constructing the state space tree using the matrices, row reduction and column reduction. And next, getting the optimal solution by comparing the nodes with the previous one, reduced matrix until 2 by 2 and constructing this state space. So this is the example. Already we gone through one example, and this is also another example for traveling salesman problem. How can we get the solutions for the state spaces after in each equation? So either you can go through the previous one or you can use this one, both are same. But in the previous presentation, that is very clear. If you want to know another example, how can we solve that clearly, you can go through it also. And next, coming to the next problem, that is the 0-1 knapsack problem. This is also solved using the two approaches, least cost search and FIFO based branch and bound. So first one, how can we solve the 0-1 knapsack problem using least cost branch and bound? So a 0-1 knapsack problem states that there are n objects given. Already we've gone through this problem in earlier methods, 3D approaches, different types. So here also, how can we solve this using branch and bound, because this is the optimal problem. So 0-1 knapsack problem states that there are n objects given and capacity of knapsack is m. Then select some objects that should fill in knapsack without exceeding the capacity of the knapsack, that is nothing but m. So this is stated as maximize z equal to p1, profit and value x plus p2, x2 plus pn, xn. WI, these are the profits and values, and these are the weights and values, where depending on the weights, WIXI plus W1X1 plus W2X2, etc. WNXN less than or equal to. So you have to maximize these profits depending on the weights that should not exceed M value. By considering x either 0 or 1, that is nothing but here we are considering whether we can accept it or you can reject it, 0, 1 accept. But here you can consider both, that is fractional and also normal. So a branch and bound technique is to find solution with an exact problem. But we cannot directly apply this to knapsack problem because this branch and bound deals with only minimization problem. So we have to modify this problem into minimization. So the problem given is maximization. So for modifying this problem into minimization, simply you can convert this, that is negate this problem. So minimization of z equal to minus p1 x1 minus p2 x2 and you know maximization and minimization already you got to operation research. So simply negate the problem, it becomes minimization problem. And the condition is say, so let c of x and u of x are the two constants or cost functions such that c of x, c exponent x less than or c dash x less than or equal to cx less than or equal to u dash x, satisfying the requirement where c of x is sigma of profits of x and u is also profits of x, but here we are calculating both c of x and c dash x, u dash x, but c dash x is the sum of the profits of the given items we have selected, including the fractional item. But u of x is excluding the fractional item. So u of x, u dash x is the upper bound and c dash x is the cost. So the c of x is the cost function for answer nodes, which lies between two functions called lower and upper bounds of the cost function. The search begins at the root node. Initially, we compute the lower and upper bounds at cost node called c-1 and u-1 and consider the first variable x1 to take a decision. Then x1 takes the value either 0 or 1, means either you can include that item in the knapsack or we can exclude that item, and continue this until we can get the optimal solution with all the items given in the set to fit in the knapsack. So compute the lower and upper bounds in each case of the variable. These are the nodes that at the first level and select the whose cost is minimum. So c of x equal to minimum of c left child comma minimum c of, that is c of left child or c of right child. In both whose is the minimum, then we can go through it. If we can get any maximum value in cost, then we can leave that. So in this manner you can continue. So the problem can be solved by making a sequence of operations as the variables x1, x2, etc. xn level wise. So a decision on the variable xi involves determining which of the values 0 or 1 is to be assigned to it by defining c of x recursively. So this is how can we construct the state space tree. Either you can accept the item or we can avoid the item. That is nothing but each node itself is having two instances, either 0 instance or 1 instance, and expand by selecting that the state space tree until we can get the optimal solution. How can we solve it with it? So here this is the problem and consider the knapsack instance. So you have to see carefully how can we get these values in the instance n equal to 4. There are 4 items and profits of those items are 10 for first item, 10 for second item, 12 for third and 18 for fourth. Carefully see. And next weights are 2, 4, 6, 9. So here we are putting the weights in ascending order. So the capacity of the knapsack is 15 M. So using the least cost branch and bound, how can we construct this space tree? So for that one, initially you have to calculate the upper bound. So for going through this algorithm, first we have to assign the variable Cp is the current profit, Cw is the current weight. This is the iteration value for number of decisions we have to take, and N is the capacity of the knapsack. So you have to pass these values. Initially these three are 0 and you have to pass N value. That is the knapsack value. So knapsack value is 15 and current profit is 0, weight is 0 and first iteration value is also 0. And next here, B equal to CP and C equal to, that is the benefit equal to CP and weight equal to C. For I equal to K plus 1 to N, we can continue until N is reached for the number of items. That is selection of items whether we can accept or reject. If C plus W of I is, that is the current weight plus the selected weight, if that is less than or equal to N, then you can add this weight to the previous one. If the condition is not satisfied, then you can reject and go for next item. And also, you can subtract the profit from the earlier one. So, B equal to B minus Pi and return B value. So, this is, we are calling this function recursively for all. So, how can we get this one? So, you have to see carefully. So, first one. At the initial stage, we have to calculate the initial C dash x and U dash x. So, first initial C dash x and U dash x. First C dash x is sum of the profits, including the fractional part also. So, here you can see profit for first one is 10 and weight is 2. You can select plus second one. Profit for second item is 10, weight is 4. So, 2 plus 4 is 6. So, you can select it. And next profit for third one is 12 and weight is 6. So, 6 plus 6, 12. And next come to profit for fourth one. That is, here the remaining space is 3. 2 plus 4, 6. 6 plus 6, 12 completed. And next we subtract that from 15. So, the remaining space is 3. So, you can get a fraction from fourth one, which is having the profit 80. So, how can we get the fraction? So, for getting the fraction, you can get, that is, what is the remaining part? 3. 3 by total weight of that object is 9. So, 3 by 9 into total profit is 80. So, 3 by 9 means 1 by 3. So, 1 by 3 into 18 means 18 by 3. So, 18 by 3 means 6. So, add this value to the current profit. So, current profit is 10 plus 10 plus 12, 32. So, 32 plus 6 is 36. So, cost is always calculated including the fractional part also until we get the M value. But U dash 1 is calculated excluding the fractional part. So, when we are excluding that fractional part, the value, profit value we are getting is 10 plus 10 plus 12, that is 32. So, the problem is minimization problem. So, the values are minus 38, minus 30. So, 10 plus 10 plus 12 plus fraction of fourth one, that is remaining part is 2 plus 4 plus 6, 12. 15 minus 12 is 3. So, weight of this fourth one is 9. So, remaining space is 3. So, 3 by 9 into the profit of that object is 80. So, the values we are getting. And similarly, excluding that fractional part item, we are getting the U value. U dash x 10 plus 10 plus 12, that is 30. So, this is the initial node calculation. Next, we can go for selection of item to fit in knapsack. So, I am going to x1 equal to 1. So, when I am selecting x1 equal to 1, when I am selecting items from the knapsack, then the costs are same, no need to calculate. When we are excluding the item, then the cost can vary. So, first choice is I am selecting x1, that is this is 1, this is 0. Expansion of this is when x equal to 1. Expansion of this is when x1 equal to 0. So, x1 equal to 1. So, the same cost values we can obtain. No need to change any. So we are considering x1, we are calculating the same. We are not excluding anyone. So what are the fractional parts? What are the whole items that may fit in the knapsack? You can consider those and you can calculate. So no one is excluded. So the calculation is similar to the previous one. But coming to the exclude part. So here see, I am excluding. That is, I am not selecting x1 equal to 1. That is the first item. Then again you can calculate removing this one. That is the first item. After removing the first one, then how can we calculate? After removing the first one, the knapsack available items are 10 plus 12, 22 plus the remaining space. So 10 plus 12, 22. What are the weights? 4 plus 6, 10. So remaining space in 15 is 10 minus 15. 15 minus 10, that is 5. So 5 by 9 into 18. So 5 by 9 into 18 means 10. So how much profit we are obtaining? 10 plus 12, 22 plus 10, 32. So that is minus 5. Remove the first item and calculate the remaining 3 which can fit in this knapsack size 50. So that is the second calculation. And similarly calculate the U dash excluding first one. So when we are excluding first one, there are 3 items, but I want to exclude third one, fourth one also because this is fractional. So the remaining profit value is for U dash, that is 10 plus 12 minus 22. That is when I am excluding x1. This is including x1. Minus 32, 22. And next, come to x2. So x1 is included and x2 is included. So value is same. I am considering x2. x1 is considered, x2 is considered, and in the remaining space x3 and 4 fraction is considered. So value is same. We are not excluding anything. If we are excluding anything, then we can subtract some value. So automatically the values can vary. So this is same when I am considering x2. x1 equal x2 equal to 1. This is x2 equal to 0. So this is x2 equal to 1. When I am excluding 2, then which items we have to consider? 1, 3, 4. So 1 is 10 plus 2 is 12 plus fraction. So 10 plus 12, here you can see 2 plus 6, 8. So remove 8 from 15. That is subtract 8 from 15. The remaining space is 7. Okay. 7 by 9. 7 by 9 into 80. So fraction we are obtaining, that is 14. So 10 plus 12, 22 plus 14, 36. And exclude this fraction, we can get 10 plus 12. So first one 10, third one 12. So minus 1. So here initial profit is, why we are not expanding these means, here the initial profit is minus 38. So the current cost we are getting the values that are greater than this one. You know, when we are considering negative values, the negative small value is greater. Negative largest value is smaller. So minus 36 is less, greater than minus 38. So this is the minimization problem. You have to select the nodes which are having the less cost than this one for minimization, optimization. So for this one, this is minus 32, no need to expand. This is minus 36, no need to expand. Then come to third node. So third node selection is also same. So 1, 2, 3 we are selecting. This is not including x3 equal to 1 this. This is x3 equal to 2. This x3 equal to 0. So when I am excluding this. When I am excluding third element, the cost is 10 plus. So you can see here weights. When I am removing 6, 2 plus 4 is 6, 6 plus 9 is 15. So you can consider 3, that is 1 2 and 4. No need to calculate any fraction because 2 plus 4 plus 9 is 15, which is equal to m. So directly we can consider both, that is minus 38, 10 plus 18, 38, and similarly this is minus 5. And next, this is when I am considering x3. x3 equal to 0. This is x3 equal to 1. So x3 equal to 1 minus 38, x3 equal to 0 is also minus 38. But here when I am considering s3 equal to 1, if I am adding the fourth node, then there is the weight becomes increased. So this should be killed. No need to consider. Then you can expand this because I am not including 3. So there are only 2 items I have been selected, 10 plus 10. 3 is excluded. Then there is a choice of selection of 4. So I am not included 3, only selected 1 and 2. And you can expand if there is a chance for adding fourth element. And also the cost value is similar to 38, we can expand. If that is greater than 38, then you can fill. But the cost is equal to 38, then you can expand. So I can select 4, x4 equal to 1. This is x4 equal to 0. So x4 equal to 1. So 1, 2, and 4. So that is minus 38 as is similar to previous one. And not including x4. x4 is not included, x3 is not included, only x1 and x2 are included here. So you can check the expansions. x1 included, x2 included, x3 included. So no need to expand further. This is, if we are including x4, the size may be increased. So kill the node here itself. So this is, the x3 is not included means there are only 2. There is a remaining space. Go for selection of x4. So when I am including x4, then I can get minus 38, minus 38. When I am not including x4, x3 is also not included. So there are only 2 items. Then 10 plus 10 and also 10 plus 10. So when x4 is not included means no need to consider the fractions also for 4. Simply calculate both. So you can continue until all the nodes that has been number of choices available for insertion of the node. So this is how can we construct the state space tree. So next one is the same. How can we calculate the constructional value? By passing the initial values for each iteration in the algorithm. So initial node is U bound, you can pass profit, cost and k value 0 and m value 15. And for second iteration, that is selection of x1. x1 is minus 10 and I is 2. That is the profit is the weight value of the profit value of x1 is minus 10, weight value of x1 is 2 and k value is 1, that is the first node. And this is no need to pass both because x1 is 0 here. Only pass value of k, that is equal to 1. And this is second iteration for the algorithm we are passing, that is second node 10 plus 10 20. So weight 2 plus 4 6 and iteration k equal to 2. And here not expanding, that is nothing but not including 2. If I am not including 2, the initial value is minus 10, profit, that is profit, and weight is 2 and iteration value is 2. And this is including 3. So minus 20 plus 12, 32. And 6 plus 6, 12. Third iteration and weight of the knapsack. And excluding 3. Excluding 3 means here including 2. So we can get this value. Minus 20, 6, iteration value 3. And next including 4, excluding 3. So here we get minus 38. Including 4, excluding 3. So 10 plus 18 minus 38. The profit is also, weight is also 15 and fourth iteration 15. And this is excluding both So minus 20, only 2 plus 4, 6, and fourth iteration 15. So this is the state space expansion. Expansion, the same values in each equation at the node expansions. So after expanding all the nodes in the tree, so what is the optimal solution we have been found? So the optimal solution we have been found is for x1, we have selected 1. So the optimal solution in the state space tree is inclusion of 1. So where we get the value 15 for weight, that is the optimal solution. In all these nodes, for which node we are getting the value 15? For 8. So what are the nodes that are expanded further that? 1, 2, that is it. 1, expand 1 included, 2 included, not including 3, 4 included. So here inclusion can be represented with 1, exclusion can be represented with 0. So x1 is included, x2 is included, but x3 is not included, x4 is included. So the profit is 10 into 1 plus P1 x1 plus P2 x2 plus P3 x3 plus P4 x4. That is here this is not equal to this is into 10 into x1 plus 10 into 1 plus 12 into 0 plus 18 into 1, that is equal to 38. So we need to consider all n items but excluding 3. So this is how we can solve the least cost set. So in this least cost set, in the state space tree, if you are getting any maximum value, simply you can prune the tree without further expansion by checking the least value less than the initial cost we have calculated at the first node, comparing that and further continue if the value of the nodes generated with the cost is less than or equal to that, then you can continue. If you are getting any node having the value greater than that, then you can stop. Here this is greater, you can stop. Here greater, this is greater, then no need to expand this. That is the least cost. Coming to the FIFO-based branch and bound solution. So here consider the same knapsack problem and also here the same. But only difference between these two is here you can expand all the nodes at each level. So first one, we are expanding, this is considering initial calculation minus 38 minus 32, considering the 3 elements, minus 38, including the fraction, excluding the fraction, minus 32, 10 plus 10 plus 12, this is u, and 10 plus 10 plus 12 plus 3 by 9 into 18, that is 6 minus 38. And these are all the nodes which are considered. Then you can expand with the same values until node 1, node 2, node 3. So node 4 is not calculated because this is filled. So this is not a feasible solution. Adding this, the size may be increased. Next, these are further expansions for each node. So when I am considering x1, this is the node. When I am considering x2, not considering x2. When I am not considering x1, but considering x2, but not considering x2. So here in this expansion, if you are getting any node greater, then you can stop. So here, when I am considering x1 equal to 0, but x2 equal to 1, we can get the same value here, no need to calculate. If you are getting false value, simply you can check here. For x1 equal to 0, x2 equal to 0, means we can consider x3 and x4. So x3 and x4 means no need to consider fractionals. x3 and x4, that is 6 plus 9, 15. So you can consider both. But the cost we are obtaining is minus 30. That is the 12 plus 18. So minus 30 means that is greater than minus 38. So fill that node. And here also minus 32. That is also greater than this one. So fill that node. And next x2, that is also greater than 38, then minus 36. No need to expand. So simply you can expand in a remaining node, that is x2 equal to 1 for further, because all these values are less than this one. But here this needs more expansions than the initial one, because for each node we have to check the two states without considering the least cost initially. If you are considering the least cost here itself, then you can prove in the previous situation. But here you have to expand and then calculate the least cost. That is only the difference between the two approaches. So here in this problem, the processing is same, but expansion is needed for each node. After expansion, we are checking whether that is further allowing any expansion or we have to kill that node or prune this. So we are continuing in this manner until nodes are missed. Now let us trace through the algorithm. Here we are using a queue instead of a stand. So initially root node is 1 to the e node. So here u of 1 equal to minus 32. So we assume that children of u are 2 and 3. So insert in the queue. And next children of 2 that are 4 children of 2 4 and 5. So insert 4 and 5 and remove 2. And next children of 3 that is 6. This is not killed, this is killed. So that is 6. And next you can remove. Next coming to the further expansion, after that you can remove 6 but that is also having the greater cost. So here node 3 is next 3 is expanded. So here what we are telling, after checking whether that is allowing any expansion or not, then you can remove. Before we cannot remove by checking the least cost. So 6 exists in the queue itself. So node 3, the next e node is expanded. Its children are generated 5, 6 and 7 and gets added to the queue. But node 7 is immediately killed as 3 of 7 is greater upper bound. So greater upper bound, not cost here. You can say greater upper bound minus 32. So here minus 32, minus 30. So simply remove this one. And next node 4 is expanded. So here minus 20, this is the upper bound, this is minus 30 is C, that is the greater upper bound means C of 7, cost of 7 minus 30 that is greater, then you can remove this. And next 4 is expanded since node 8 and 9 are generated and are added to the queue for 4. 8 and 9 are generated with the values that are similar to the previous one, then you can continue in the queue. Then you can check is there any expansion of 5 and 6. So the upper is updated, that is 9 is u of 9 is equal to minus 38. But node 5 and 6 are next to 2 nodes to become e nodes. But neither one is expanded because both 5 and 6 are having the value greater than upper bound value. So node 8 is the next e node. So here already removed elements are 5 and 6 eliminated. So next coming to the node 9 is minus 38. So node is next node is when 9 retains. Next node is 8. 8 is the e node. The branches of 8 are 10 and 12. So here 10 and 12 expanded further. So 10 is not feasible. So branch of 8 that is removed and branch of 8 10 that is removed and branch of 8 11 which is also having the upper bound, that is here you can see after expand there are nodes in the after removing 5 and 6 nodes in this one is 8 and 9. So get first e node 8 and remaining one is 9. So childs of 8 10 and 11. So 10 is removed because this is infeasible and 11 is having the upper bound, both are eliminated. 11 is having the same cost but not feasible value because that is having the upper bound value greater. One value is equal but upper bound value is greater. So this is also eliminated. And next coming to 9. Childs of 9, 12 and 30. So upper bound for 12 is minus 38. This is existed. And next coming to the 13. 13 is still because it cannot be there are the, after when we are crossing 9 we are inserting 12 and 13 in the queue, but 12 is insert, well, 12 can exist but 13 cannot exist because that is already having the upper bound greater than the upper bound greater than the initial upper bound value 38. So simply remove this one, and next, because when we are selecting 12 there are no further nodes for 12, no items available with you, then the queue is empty, you can stop here. Here the values we are obtaining, x1 is selected, x2 is selected, no x3, and x4 is 1. So this is the solving the knapsack problem using least cost form. So here another example problem. So you can see this example also similar to the previous example of this cost 901 knapsack. Here the values are changed. This is not the previous one. With 5 items we have been inserted a new one. So these are all some important questions you can observe and you can solve. So this is the branch and bound. How can we solve the traveling salesman problem and also 01 knapsack problem? But traveling salesman problem cannot be solved using the FIFO approach, but we can solve using only the least cost set. But here 01 can be solved using both, but both are in both two. So when we are comparing, the further number of expansions in least cost is less than the number of expansions in FIFO. So least cost is better than the FIFO set. And also here, after checking the nodes whether those are upper cost or not, then you can eliminate from the queue. But in least cost, before expansion itself, by checking the cost simply, we can eliminate further expansion. So that is the main advantage of comparing these two approaches. So this is up to first part of fourth unit, that is the branch and bound techniques. And the last part in fourth unit, that is the NP hard and NP complete problem. You can see it now.